Okay, thanks for the introduction. Yeah, my talk is about TreatJS, a higher order contract system for JavaScript. Sorry, okay. Okay. So in general, a contract specifies the interface of a software component by stating benefits and obligations for the component's user. TreatJS is a language-embedded higher order contract system for full JavaScript, which enforces contracts by runtime monitoring. It is implemented as a library, so it can easily be included in existing web projects, and all aspects of the contract API are accessible through a contract API. TreatJS is inspired by existing contract systems, so it supports the standard abstraction for higher order contracts, base contracts, function contracts, dependent contracts, as introduced by Findler and Felleisen in 2002. TreatJS novel contributions are its support for contracts in the form of intersection and union, and for arbitrary Boolean combination of contracts. Its guarantee of a side effect-free contract assertion, so the evaluation of a fulfilled contract did not influence the normal program execution, and its notion of contract constructors that generalize dependent contracts and that are the building blocks for parameterized contracts, contract abstraction, or recursive contracts. First, I will recapitulate base and function contracts, and then I will go to the new features of TreatJS. As in other contract systems, predicates are the fundamental building blocks of all other contracts. And in TreatJS, a predicate can be specified by using plain JavaScript functions. So, for example, here the isNumber function, which checks if its argument is type of number. So each predicate uses the full expressive power of JavaScript. And at the end, to create a base contract from such a predicate, we simply apply the corresponding constructor to it. Here, contract is the object that encapsulates the whole contract system, and its assert function attaches the contract to a value. It first takes the subject, the value to which the contract is asserted, and second the contract. And the contract assertion of a base contract either raises a contract violation or returns the value itself. So for a number value, the number contract is satisfied, but for a string value, the number value is not satisfied. The contract system blames the subject because the predicate did not return true. TreatJS also provides contracts for functions, and as a running example, I consider the plus function, which takes two arguments and applies the JavaScript plus operator to its arguments. And a sensible contract for this plus function is a function contract that, for example, restricts the domain of the function to number values and that guarantees that the function has to return a number value. To create a function contract, we simply use the function constructor. The constructor takes first an array with 0 and more contracts for the domain of a function, one contract for each argument, and one contract for the range of a function. Now if we call our contracted function with two string values, the contract system blames the context for providing a wrong argument, because the context gets blamed for a function contract exactly if the argument gets blamed for the domain contract. In this case, it gets blamed as the subject. And on the other side, now we consider a little bit broken version of the plus function that first checks if both arguments are bigger than 0, and in case one argument is not bigger than 0, it returns a string. And we would call this function with 0 and 1. The contract system raises a violation and blames the subject because the context gets not blamed for its argument, but the function return gets blamed for the range contract. The subject gets blamed, sorry. Now let's go to some new features of TreatJS. As we've seen in the example before, we call the plus function with two string values, and the contract system blames the context for providing a wrong argument. But we also know that the plus operator works for strings too, so we need something that allows us to model overloading and multiple inheritances. So in TreatJS, we can assign it an intersection contract, which is inspired by the corresponding operator in type theory, intersection types. And as for intersection types now, the context may choose either to call the function with number values or string values, and the function has to handle both inputs. Here now we will assign it an intersection contract, an intersection between two function contracts, exactly one for number values and one for string values. And this can be done by using the intersection constructor that takes two arbitrary contracts. And now if we call our plus function with two Boolean values, the context gets blamed for providing a wrong argument, exactly because the context gets blamed for an intersection contract if it gets blamed for C and it gets blamed for C prime. And if we assert this contract to our broken version of plus and we call the function again with 0 and 1, the contract system blames the subject because, as I mentioned before, the function needs to handle both inputs, and for number inputs it has to return a number value, but in this situation we return a string value. So the subject gets blamed if it gets blamed for C or it gets blamed for C prime. Unions are the dual of intersection contracts, and again there is a connection to union types. Now we would specify a sensible contract for our plus broken function, and the first idea could be to assign it a union contract between two function contracts, one that takes number values and returns a number value, and one for numbers on the domain and a string on the range. As before, we can construct the union contract with the union constructor that takes two arbitrary contracts. And now if we call the plus broken function with two strings, the context gets blamed exactly because the context gets blamed for C or C prime in our situation. And as I mentioned before, the subject of a union may choose either to fulfill the left or the right side, but there's something that is special with union contracts. If we first call the function with two number values, the function returns a number value, and a second call that returns a string value did not satisfy our contract. Let's talk about the contract assertion. The presence of operators like intersection and union requires that a failing base contract did not throw a violation immediately if one contract fails. So for example, the add one function here in this example contracted with an intersection contract between two function contracts, one for number values and one for string values. And if we call this function with a string A, the left function contract fails and blames its context for providing a wrong argument, but the right contract succeeds. And in this case, because the context of an intersection may choose either to fulfill the left or the right side, the contract is satisfied. So the final violation of such a contract depends on failures in different subcontracts. And to assert contracts correctly, the contract system must keep track of each contract and must connect each contract to the enclosing operator. This connection is implemented by so-called callbacks. Each callback implements a constraint that specifies the outcome of a particular contract in terms of its subcontracts and links the outcome to the enclosing operator. There is at least one callback for a contract, and there may be multiple callbacks for delayed contracts, function contracts, for example. Each callback reports a record consisting of two fields, a context field and a subject field, and the meaning of the fields is as follows. If the context field is false, then the contract fails and the system blames the context, whereas if the subject field is false, then the contract fails, blaming the subject. Both fields range over the set B4. This is the lattice underlying Belknap's four-valued logic, and the lattice is intended to deal with incomplete and inconsistent information. It contains the elements bottom or unknown. This indicates that we do not have enough information or the contract is not evaluated so far. False is false, true is true, and top is the merged outcome for delay checking of function contracts. If the function first evaluates to true, and another time it evaluates to false, and in some situation we need to remember the previous results. Yeah, to demonstrate how the callback structure works, we consider now a little bit broken version of the add1 function that is also contract with the intersection contract from before. Two function contracts, one for numbers and one for string values, but it applies its argument to it applies the plus operator to its argument and the string one, so it always returns a string, and this function did not satisfy the contract. But if we only call the function with string values, we will never see this violation. So in our example, we first call the function with a string value, and in this situation we did not see the violation, and a second time we call the function with a number value, and in this situation our contract system will blame the subject. Callbacks build some kind of tree structure that is rooted in the contract assertion itself, and because we assert a delayed contract, callbacks first create a collecting node that merges the outcomes of different delayed checks. The record consisting in the callback is undefined, undefined. The first field is the context field, and the second is the subject. Yeah, and now the contract is not evaluated. Then if we start calling the function with a string a, we first need to create a structure to handle the intersection. This is created now. Then next we create a structure to handle the both function contracts. And then we start with checking the domain contract of the right function contract. This is the contract that checks for strings. Okay, we call our function with a string value. So this contract is satisfied, and it updates true to the function contract. But the function contract still needs to wait until its range part is evaluated. Next, we evaluate the domain of the left function contract. This checks for number values. Okay, we do not have a number value, so this base contract fails, and it blames its subject. So it reports true false to the function contract. Yeah, and because the domain or the subject of the domain is the responsibility of the context of a function, and yeah, we call the function with the wrong argument. So this function contract blames its context, and it reports false true to the intersection. Yeah, but the intersection still needs to wait until it has results from the right function contract. Then next we check the range of the left function contract. Because the function returns a string, this base contract is also not satisfied. It blames its subject, and it reports true false to the function, and the function contract did not do anything else. Yeah, and finally we check the range contract of the right function contract. This checks for strings. Okay, it is satisfied, it updates true to the function contract. Now the function contract updates true to the intersection. And yeah, because the context of an intersection may choose either to call a function with number or string values in this case, the intersection is satisfied, and it updates true to the collecting node. Yeah, now we start with the second call, where we call the add1 broken function with a number value. The collecting node still knows the result from the first execution, and as before, we need to create a structure to handle the outcomes. Yeah, and then we start with checking the domain of the right function contract. This checks for strings. We do not have a string, so it blames its subject and updates true false. And as before, the function contract now updates false true to the intersection because the context provides a wrong argument. Next, we check the domain of the left function contract. In this case, we have a number value, so this contract is satisfied, and it updates true. But our function did not return a number value, it returns a string. So the range contract is not satisfied. It blames its subject because it's a string. And now the function contract knows that the return of a function is the responsibility of the subject. So it blames the subject and reports true false to the intersection. Yeah, and the subject of an intersection needs to handle both inputs, and it has to return a number value in our situation. So the intersection updates true false to the collecting node, which merges the outcomes of all calls. Yeah, and in this situation, our contract system rises an exception and blames the subject. yeah, let's go to some other features of TreatJS. As mentioned before, predicates use the full expressive power of JavaScript, but predicates are also intended not to interfere with the normal program execution. So our solution is TreatJS consists of a sandbox, and each predicate is evaluated in a sandbox. So for example, the damaged predicate is number here in this example, where in line 2 a programmer carelessly omits the var keyword in front of the type variable name. Yeah, and if we create a base contract from such a predicate, and if we assert this contract to some value, the predicate is evaluated, and yeah, when evaluating the predicate, it attempts to write to the global value type. But in TreatJS, the sandbox reopens the predicate and removes all external bindings, and yeah, in this situation it would throw an access violation. However, read access is safe, and many useful contracts require read access to some global values. So for example, the array contract that checks if its argument is instance of array. Without giving a concrete permission, our sandbox would reject such a predicate, and we are not able to state such predicates. Yeah, to grant read access, TreatJS consists of a with contract, which is very similar to the with statement in JavaScript. It first takes a binding object, and second a contract, and each binding defined in this object is then available inside of the sandbox and can be accessed by the predicates. So for example, we can now use the global array element by using outside array inside of our predicates. Clearly, all values that are passed to predicates, either as an argument or as some binding, is wrapped in a proxy membrane to at the end guarantee write protection. Another point, because some contracts need to store some data for later use, for example, contracts that depend on the function input, or parameterized contracts, or contracts that need to store some values from previous executions. All these contracts require to store some data without interfering with the normal execution.
I have a question.
Okay.
Could you back up to the slide with the contract with outside arrays?
Yeah.
Is this microphone on?
No.
Are we turning on?
But I hear you.
Okay, I will speak loudly. So having given this contract access to the array through outside array, having given this contract access to array through outside array, how do you even express? How does this express that the contract cannot modify array or array.prototype? And how does it enforce that constraint?
So this array object is wrapped in a JavaScript proxy, which at the end implements an identity-preserving membrane, and this guarantees that if one would modify the object inside of the predicate, then also the sandbox rises in violation. Or, okay?
Please continue.
Okay. Yeah. Yeah, we need something that contracts are able to store some data for later use or for whatever they want. In TreatJS, this can be done by contract constructors. Constructors take a constructor function with some arbitrary number of arguments, and like predicates, this constructor function is first evaluated in a sandbox. But unlike predicates, the constructor function may contain contract definitions, and finally it has to return a contract. And yeah, every predicate that is specified inside of such a constructor function is guaranteed to be without references to the outside world, so there is no need to evaluate such predicates in the sandbox again. But each predicate that is defined inside refers to variables and arguments of the constructor function. So for example, here we have some parameterized type contract that whose constructor function first takes some type information, and it finally returns a base contract that exactly checks if its argument is is type of equivalent to this type information. Yeah, and now at the end we can unroll this constructor by calling it with some concrete type information, and we receive our number contract as in the examples before. Another use of constructors is contract abstraction, which is very similar to polymorphic type. So for example, a sensible contract for our plus function could be to specify that both arguments have to be of the same type, and the return has also be of the same type as the argument values. In TreatJS, we can construct this by using a constructor that first takes some arbitrary contract, for example, and that returns a function contract with exactly this contracts in place. Yeah, and because constructors are contracts, they can be asserted to values as contracts are, but instead of resulting in a contracted version, we now result in some kind of abstraction that first needs to be called with some concrete contract, here for example our number contract, and then we can call the plus function with 2 number values. Another use of constructors are dependent contracts. A dependent contract is a function contract where the range of a function depends on the function input, the range contract, and the contract for the range of a function can be constructed by a constructor call that is invoked with the function input. And exactly in this way, TreatJS builds dependent contracts. So here in this example, we build a constructor over 2 arguments, x and y, and return a base contract that checks if all arguments and the return have the same type. Yeah, and then if we construct a dependent contract by this constructor and we call the plus function, the constructor gets called with the both arguments and returns a contract that at the end is asserted to the return of the function. In this case, I have to mention that there is no check of the domain of the function, but if we will check the domain, we can easily combine this dependent contract by using a conjunction with some other function contract, for example, that also checks the domain. Yeah, that brings me to the end. Let's conclude. We have seen TreatJS, a language-embedded dynamic higher-order contract system for full JavaScript. We support intersection and union contract and arbitrary Boolean combinations of contracts. We have a systematic blame calculation. We have a compositional sandbox that guarantees non-interference. And we have contract constructors that are the building blocks for recursive contracts, parameterized contracts, contract abstraction, and so on. Yeah, thank you for your attention.
I actually did not understand the answer to my previous question. I want to follow up. If you wrap array, but you prevent modification to array.prototype, then you have to wrap array.prototype as well. If you wrap array.prototype, you have a different identity. Instance of makes use of primitive identity, which means a primitive array would not be instance of a wrapped array. Would not be instance of when you check against the wrapped array.prototype.
The argument of the predicate is also wrapped in a proxy membrane, and I think the instance of check is not trapped by the proxy handler. So this works. Or yeah.
So this is a nice piece of work. In a way, I think you've undersold yourself. I first saw this problem in May 2014 in Japan, when David Van Horn said, okay, here's something we might want to do with union or intersection. And look, there's no way of dealing with this, because it's wrong to blame the subject and it's wrong to blame the context. And then my student, Jakub Zaluski, solved this, and you solved this, both with a very nice idea, which is blame both. And so that's a very nice insight, which I'm afraid didn't come across clearly in your talk. So I wanted to bring it out, because I think that's a great insight that you guys have had.
Okay.
But I also wanted to ask a question. You didn't say anything about performance. The last talk was motivating performance. And of course, it's really important early on to look at performance and things like this, because we will get absolutely crap figures. And that's great, because the really poor performance then encourages future work that can improve on it.
Yeah. Yeah. Yeah, at the end, each predicate is a function call. So the performance impact depends on how many predicate checks occur during a program. So yeah, if you have 1,000 checks, then you have 1,000 additional function calls at the end. It is not really expensive.
Have you evaluated an actual
I have some numbers, but it's hard to explain the numbers. I can show you the numbers offline if you are interested.
So your implementation of intersection contracts seems like it potentially delays when you report an error later than you would have had if you had simply had a standard function contract. Are there cases, can it delay things unboundedly far into the future, or further than the standard Findler-Felizen semantics?
Yep.
Your answer to the performance question is wrong. You need to remove all predicates, have no predicates called whatsoever, and measure the overhead of the mechanism that you impose. So can you then at least indicate what those numbers are if you use any predicates?
Sorry, I don't get the question. What is the question?
Your answer to the performance question was, it depends on the number of predicates that you call.
Right.
That's wrong. What you have to do is you have to replace the predicates with the any, or whatever you call it, base contract, and then measure the overhead of the mechanism. Your advisor says you've done so. Why don't you give the right answer then?
Yeah, right. We have to do both. We have one evaluation that only checks the predicates, and we have done one run where we replace the predicates by only true and measure only the impact of the contract system. It's acceptable for. It's okay. I do not have detailed numbers now, but you can. But you can look at the paper, and there are concrete numbers.
Thank you. We have time for one more question. Okay, good. Thank you.